more. In this video, we will learn about routing. Students will be able to explain the concept of routing and identify efficient routing protocol. Mobility solution consider technique for preserving the IP address of a node as it moves from one point of attachment to another, along with methods for forwarding traffic to a node while roaming and performing route optimization. IP routing, on the other hand, deals with maintaining routing tables on IP routers, which indicates which next forwarding decision should be made for the destination of an IP packet. IP routing protocol maintains this routing table using a wide variety of techniques ranging from ad hoc dynamic routing for wireless mesh network to path vector interdomain routing on the core internet. In this section, we examine the basics of IP routing for 6LoWPAN along with the state-of-the-art techniques currently used or in development. Other techniques performing mesh topology below the IP layers such as link layer mesh and low-PAN mesh address techniques are not considered here. When discussing IP routing for 6LoWPAN, there are two types of routing which need to be considered: routing inside a 6LoWPAN and routing between a 6LoWPAN and another IP network. Routing is challenging for 6LoWPAN with low power and low C radio links, battery power, nodes, multi-hop mesh topology, and frequent topology changes due to mobility. Successful solution must take the specific application requirement into account. Along with internet topology and 6LoWPAN mechanism, such a solution is being developed by the routing over low power and low C, that is ROLE, network working group at the. In this section, we cover the requirement route matrix architecture and algorithm for ROLE. Relevant support mechanism and routing algorithm have also been developed in the IETF Mobile Ad Hoc Network Working Group. Two kinds of routing can be performed with 6LoWPAN: intra-LoWPAN routing between 6LoWPAN routers and border routing performed at the edge of the 6LoWPAN by the 6LoWPAN edge router or an IPv6 router on the backbone link for extended 6LoWPAN. There are two main classes of routing protocol useful for 6LoWPAN: distance vector routing and link state routing. An analysis of existing distance vector and link state routing algorithm along with their applicability to wireless embedded application is available. Distance vector routing. These algorithms are based on variation of the Bell-Fover algorithm. Using this approach, each link is assigned a course using appropriate route matrix. When sending a packet from node A to node B, the path with the lowest cost is chosen. The routing table of each router keeps soft-state route entries for the destination it knows about with the associated path cost. Routing information is updated either proactively or reactively depending on the routing algorithm. Owing to their simplicity, low signaling overhead, and local adaptive nature, distance vector algorithms are commonly applied to 6LoWPAN. Link state routing. In this approach, each node acquires complete information about the entire network called a graph. To do this, each node floods the network with information about its link information to nearby destination. After receiving link state report from sufficient nodes, each node then calculates a tree with the shortest path from itself to each destination using Dijistra's algorithm. This tree is used either to maintain the routing table in each node for hop-by-hop forwarding or to include a source route in the header of the IP packet. Link state algorithms incur a large amount of overhead, especially in networks with frequent topology change. They require substantial memory resource for the amount of state needed by each node. Thus, they are not suitable for distributed use among LoWPAN nodes. Proactive routing. Algorithms using a proactive approach build up routing information on each node before the routers are needed. Thus, they proactively prepare for the data traffic by learning routes to all possible or likely destinations. Most protocols that are used in inter-domain or intra-domain IP routing use a proactive approach as topologies are stable. Examples of proactive algorithm can also be found from MANET, for example, optimized link state routing and topology dissemination based on reverse path forwarding. Reactive routing. Reactive routing protocols store little or no routing information after auto-configuration of the routing protocol. Instead, routes also discover dynamically only at the time they are needed. Thus, a process called route discovery is executed when a router receives a packet to an unknown destination. Examples of reactive algorithm includes the magnet ad hoc on-demand distance vector and dynamic magnet on-demand protocol along with the Zigbee routing algorithm derived from ad hoc on-demand distance vector. The advantage of this approach is that signaling and route state grows only as needed, and it is especially when suited to ad hoc network with frequent topology change and mainly peer-to-peer communication. MATNET has also produced valuable work on basic mechanisms for supporting routing in this environment. A common packet format for use by all MATNET protocol has recently been developed. As an addition to this, a standard time representation has been defined. Finally, a two-hop neighborhood discovery protocol is currently being developed for use in collecting routing information in a standard way. The protocol and mechanism developed in MAGNET can be applied to 6LoWPAN network. They are especially useful for applications with very similar requirement of typical MAGNET application. The biggest challenge for applying a MAGNET algorithm to 6LoWPAN is in reducing the overhead of signaling packet and simplifying the algorithm. The common magnet protocol format and two-hop entry can also be usefully applied to new routing protocol for 6LoWPAN. The system requires high internet connected network with strong error node-to-error traffic flows along with the need for multiple routing and often traffic engineering. A new reactive distance vector routing protocol called the dynamic magnet, making improvement on previous protocols such as ad hoc on-demand distance vector and dynamic source routing. This protocol make use of the same types of route discovery and maintenance message as ad hoc on-demand distance vector. The main improvement compared to previous work include improved convergence in dynamic topologies, use of the common magnet packet format, support for a wide range of traffic flows, consideration for internet interconnectivity, take hosts and routers into account.